Imagine a material stronger than steel, yet lighter than a feather, and woven effortlessly by tiny spiders. Sounds like science fiction, right? But it's real, and it's called spider silk. Today we're diving deep into the secret chemistry that makes spider silk not just strong, but mind-blowingly resilient. Most people think spider silk's strength comes from its physical fibers alone, like how steel beams hold up buildings. They picture spider silk as just tiny threads spun really tightly, the way cotton threads in fabric might get stronger if you pull them tight. So the assumption goes, it's all about the way the fibers are arranged and the sheer tightness of the silk strands. But that's only part of the story. The real magic lies in the chemistry hidden within these fibers. Spider silk is primarily made from proteins called spidroins, which are long chains of amino acids. These proteins don't just form a simple thread, they fold and organize themselves into precise molecular structures that combine flexibility and strength in an almost perfect balance. At the microscopic level, the silk contains tiny crystalline regions interlinked with amorphous or non-crystalline parts. The crystals act like rigid building blocks, giving the silk its incredible toughness. Meanwhile, the amorphous sections provide elasticity, allowing the silk to stretch without breaking. This balance means spider silk can absorb great amounts of energy, much like a shock absorber, which is why it outperforms steel in tensile strength. However, the secret doesn't stop there. The real edge comes from hydrogen bonds. Think of them like millions of tiny Velcro strips holding the molecules together. When pulled, these hydrogen bonds break and then quickly reform, allowing the silk to stretch and then snap back to shape without losing integrity. This dynamic bonding system is what grants spider silk such a remarkable combination of strength, flexibility, and resilience. Imagine a steel wire snapping once it reaches its limit. Spider silk, on the other hand, can stretch up to 5 times its original length before breaking, thanks primarily to these reversible hydrogen bonds. This molecular dance ensures the silk is both strong and tough, traits that steel simply can't match at such lightweight scales. To put it in perspective, spider silk has a tensile strength of about 1.3 gigapascals, which is stronger than most steels used in construction. And it's incredibly lightweight. Its density is about 1/4 that of steel. This unique chemistry has inspired scientists who want to mimic spider silk for real-world applications. For example, in the medical field, synthetic spider silk is being researched for use in strong sutures that heal wounds without irritating the skin. It's biodegradable and biocompatible, meaning it can work with our bodies naturally. Another fascinating application is in creating ultra-strong and lightweight body armor, potentially revolutionizing personal protection equipment for soldiers and law enforcement. A third exciting area is in sustainable textiles. Companies are experimenting with spider silk protein to create clothes that are both durable and eco-friendly, reducing reliance on plastics and heavy manufacturing processes associated with synthetic fabrics today. So why does all this matter? Understanding spider silk's chemistry doesn't just satisfy curiosity about a strange spider's web. It opens doors to materials technology that could transform many industries. Imagine cars made lighter and stronger, bridges repaired with self-healing fibers, or surgical threads that improve healing. All possible by unlocking secrets coded in spider silk. The story of spider silk is a perfect reminder that nature often holds the answers to problems we think are purely human. Its secret chemistry is a powerful example of sustainable design, combining strength, lightness, and adaptability in ways our current steel and plastics struggle to match. Next time you see a spider's web glistening in the sunlight, remember, you're looking at something that's not just incredible in beauty, but a masterclass in molecular engineering. That invisible chemistry, this secret dance of proteins and bonds, could well be the blueprint for the next generation of materials that change how we live, work, and build our world.